So we had derived this result before the break. Now let me just emphasize that these three equations here correspond to the general case, where we have no restriction on the velocity. This formula applies only for a small velocity compared to the speed of light. But it's nevertheless important because it gives us the lowest order relativistic correction. And so this would be the first correction you obtain when including the lowest order in the velocity. And a scenario where this is relevant is, for instance, electrons moving through solid state materials, because the velocity of these electrons is often characterized by the Fermi velocity. And this can typically be 10 to the power of 6 meters per second in some cases. And so we see that VF being the Fermi velocity of C, is about 1%. So it's small, but there's still a finite correction, actually due to relativistic effect. So what does this mean? Well, it means the following: that if you have a particle that is moving in a region where there is no electric field, that particle will nevertheless experience a net electric field if there is a magnetic field. So even if the electric field is zero, the electron feels an electric field if it's moving in a magnetic field. It has to be a charged particle. So even if the electric field in our system is zero, the electric field experienced by the particle is not necessarily zero. So that was for the electric field. Now we can consider an analogous result for the magnetic field as well. If we make a similar analysis as we did for the electric field, in effect considering two specific indices for this field transformation, for the transformation of the electromagnetic field tensor, we would arrive at these general equations. So we see that they have a very similar structure. And in fact, well, one important similarity is that the component of the magnetic field along the direction of relative motion is the same. It's invariant. Now, if we perform a small velocity expansion of these general results, we get the following. So you can note the analogy here with the electric field. From this result, we can now draw an important conclusion. So just like in this case, we now see that a particle moving in a region where there is an electric field but no magnetic field will still experience a net magnetic field dictated by this term, even if the magnetic field is zero. So a charged particle moving in a region with a finite electric field but no magnetic field will nevertheless experience a net magnetic field in its rest frame. I mentioned to you that this has important physical ramifications, and actually we can understand the phenomena of so-called spin-orbit coupling from this equation here. Are you familiar with spin-orbit coupling? Vaguely heard the term, perhaps? Okay, so let me just go through it quickly. We can start by the observation that if you have a particle such as an electron with spin, we know that spin interacts with the magnetic field. So the Hamiltonian describing this so-called Z-man coupling can be written quite generally, something like as follows. So alpha is the coupling constant here. S is the spin of the particle, for instance the electron, and B external is the external magnetic field. So you see that depending on the sign of alpha, the spin will prefer to be oriented parallel or anti-parallel to the magnetic field. All right, so according to this resultant, if we have an electron moving in an purely electric field, even if we apply no external magnetic field, and the electric field then comes from, for instance, the atoms around it, we said we get this term. This term has to be included in the Hamiltonian to describe the motion of the electrons. So we get this Zeeman coupling term, where this field is now not an external field, but this field perceived by the electron moving. So in fact, we get something like this. So you get a velocity-dependent magnetic field. You can think of this as a magnetic field that changes direction depending on the direction of the electron, due to the velocity here. And this is where the name spin-orbit coupling derives from, namely that there's a coupling, there's a relation between the spin of the electrons and their orbital motion, their velocity, for instance, in this case, how they move. And this is precisely a relativistic effect. Spin-orbit coupling is a relativistic effect. So we see then that this has important physical ramifications. I mentioned to you that we take a look at an example of why the electric and magnetic field transform in the way they do. So I'll give you an example which might be helpful in order to understand why they transform as they do. For instance, leaving the components along the direction of relative motion invariant. So it's by no means a proof, but it might help to see where, or give an intuitive way of thinking of the transformation. So you consider, for instance, a surface where you have a lot of point charges. So you have a conductor and you have all these point charges here, which may be electrons, for all we know. And so this is our lab coordinate system. And we now introduce a moving reference system, which is moving in some direction. So we have coordinate system like this, for instance. So what we know then is that depending the components of the electric field from the surface of point charges should transform differently. So what happens if this coordinate system, S prime, moves with velocity along the x-axis? Yep.
Is there a reason you have a left-handed system?
X, y isn't, so this means out of the board, right? Oh, sorry. Yeah, that was a bad choice. Should like this. So consider S prime moving along the x-axis. all this surface with point charges now gives rise to some kind of electric field. We don't know exactly what the electric field is. It would depend on the distribution of these charges, how strong they are, etc. But we can still say something about the situation. In other words, what kind of electric field would an observer in S prime feel if he's moving in this direction? So we can start, would he feel the same or would he feel a different electric field?
In that direction?
Mm-hmm.
Well, it would feel the same.
Okay. And how do you reason?
Well, if the potential from point charges decay 1/r, then it should be on a constant potential that way.
Right.
Approximately, at least.
So I agree, if we had only one point charge, then the potential would go with 1/r. And yeah, it would decay like 1/r. But in general, we have some distribution here. So for instance, the electric field here should be different from here. Right? Because we have more charges here than here. It's not completely symmetric. Well, let me pose the question a bit differently. What kind of relativistic effects does an observer here see with regard to this system? So here we have some distribution of charge. So we have some charges. If we now consider a top view, let's say they are neatly arranged like this. So they have a separation here, L, 0. Well, the point is that if this guy is moving with respect to the system here, with a velocity that is comparable to the speed of light, or at least if we take into account the first order correction, the relativistic correction, we get the phenomenon of length contraction. So he actually observes a different charge distribution than what we have here, because the distance between the charges isn't the same anymore due to length contraction. So the component of the field, the components of the electric field in this plane will be different as seen from this guy's point of view, compared to in our lab system. And in fact, they will transform just according to these formulas that we derived. On the other hand, we see that if this coordinate system is moving along the z direction, there is no length contraction. The observer here and here completely agree on the charge distribution on the surface here. And so they observe the same electric field. So the point that I would like to emphasize here is that you can partially understand this phenomenon of why the fields transform the way they do by considering these a thought situation with a charge distribution. Because once you have a charge distribution, you have to take into account the phenomenon of length contraction. And then you can see why in certain directions you have a transformation of the field and why in others you don't. So this is by no means a general situation, but it was just meant to illustrate how you can think about it intuitively. So if I'm not mistaken, there are some more general arguments in the book by Goldstein. Okay, we're going to change topic and discuss something which is known as canonical transformations. This is in fact the final chapter or final topic in this course. Now, canonical transformations are linked to the Hamiltonian description of classical systems, of mechanics. So we're basically going to revisit our old friends, the Hamiltonian and the Lagrangian formalism. And as we've seen previously, one of these two formalisms doesn't necessarily have an advantage compared to the other one in terms of allowing us to solve the system more easily. They provide two complementing approaches to our problem. One of them involves second-order differential equations, the other one first-order. But then you also have a difference in what kind of generalized coordinates you use to describe the problem. You have Q and Q dot in Lagrangian, and you have Q and the canonical momenta in the Hamiltonian formalism. So which approach you use, it's pretty much the same for at least the type of problems we've been considering so far. So we state like this. However, there are areas of physics where the Hamiltonian formalism is more convenient for the reason that it uses the generalized, for its generalized coordinates the position and the canonical momentum. So the Hamiltonian formalism is often used in statistical mechanics and also quantum mechanics, because in those theories it's often advantageous to use the canonical momentum as a fundamental variable describing the system. Now, to see what these canonical transformations are all about and why they are useful, we'll just briefly start by reminding ourselves of the description we have so far. So we have been talking about this phase space, which is spanned by two n-axes. We have n-axis for qi and n-axis for pi. So the canonical momenta may be obtained if we know the Lagrangian of the system as follows. So it will be a function in general of q, q dot, and time. Now, we can also express this in terms of Hamilton's equations. Like this. So just to remind ourselves that the Lagrangian is a function of q, q dot, and time, the Hamiltonian is a function of q, canonical momentum, and time. And the link between these quantities is obtained by Hamilton's equations. And more formally, the way we went from the Lagrangian formulation to the Hamiltonian formulation was to use this Legendre transformation, basically consisting of setting the Lagrangian equal to the Hamiltonian minus the product between the variables we wanted to exchange. So let me give you an example of a transformation that we can do in terms of the coordinates. Namely a point transformation. And what this means is that we introduce a new set of these position coordinates, large qi, which is a function of the old ones. Can you think of any example of a point transformation?
Lorentz transformation?
Absolutely. So in that case, we introduce a new set of coordinates, which are functions of the old ones and time, possibly. Another example is going from Cartesian to polar coordinates. So we have, in that case, something like this. So that's a point transformation. However, we can make this more general and still be in accordance with these fundamental principles in classical mechanics. Namely, we can introduce a transformation of both these spatial coordinates qi and the momenta pi. So keep in mind that in the Hamilton formulation, the q's and p's here are treated as independent, but what's the word? Likeverdige. Equal, yeah. They're considered on equal footing coordinate. So in principle, we should be able to transform both q and p. So that might look something like this. So we're actually introducing a set of coordinates here which depend on both the old coordinates and momenta. And similarly, momenta which depend on q and p. So this is no longer just a new description of space, as in this case with polar coordinates, but it's a transformation of the entire phase space. So I realized that it might be a bit tricky to get a grasp on what this means or visualize this. I mean, how do you visualize? Okay, so this is easy enough. We can imagine this radial vector, how it depends on x and y and the angle, etc. But having a position vector that depends on both the old positions and the old momenta, well, that's more tricky to see. Yeah.
Can this be considered an analogy to Gaussian variance in the Lagrangian formalism?
How do you mean?
In the Lagrangian, we could add arbitrary
All right.
time derivatives
Mm.
of functions without changing the equations to motion. And here you can't do that with the Hamiltonian, but you can transform the coordinates instead.
Yeah, you're absolutely right. So I'm not sure we call it a gauge invariance. Well, maybe, it depends. Okay, so if you're using a field description of Lagrangian, well, maybe you can choose a gauge for the fields in a sense. But as you say, we will see that this can actually be interpreted as an extra term in Lagrangian, which doesn't change the physics. But we'll get to that. So for now, just think of these as a mathematically allowed transformation, which is consistent with our description. And it's not meant to be easily visualized, for instance. So even though it might be hard to visualize what that means, we will see that this mathematical possibility of making a canonical transformation gives us a great help in solving certain types of problems. Now, what's important here is that when we make this set of transformations, then the large Q and large P still have to be canonical variables. I mean, we can think of 1,000 ways to make such a transformation, right? But to have a transformation that is consistent with this whole Hamiltonian framework, having satisfying Hamilton's equations, etc., these transformations have to satisfy specific rules. So these quantities Q and P are canonical coordinates which satisfy a new set of Hamilton's equations, which have exactly the same form as the ones we're used to, but instead of H, we're now using K, where K is the Hamiltonian, but expressed in terms of these new variables. So basically by substituting our transformation equations into the old or original Hamiltonian. So the main message here is that this set of transformations is a canonical transformation if the new coordinates satisfy these equations where K is it's the Hamiltonian expressed in the new coordinates. So let me just write that here. So it's important to note here that any transformation is not necessarily a canonical transformation. But a transformation of the type 1, indicated over there, is a canonical transformation if this is satisfied. So we'll continue to build on this tomorrow.